for students, but it's 5 p.m. and I'm going to start. And just this week, I was waiting for the homework that I sent an email to everybody and asked, let me admit this too. And I emailed everybody and I asked to work on that, because this part is very important. Is part of your this is part of your exam for the second exam, and very important part of the exam. And because of that, I emailed everybody and I asked to spend time on this weekend and work on it and send it to me. Unfortunately, so far, less than 1/3 of the class work on this and send that to me. Thank you for all those that they work on deflection uh, calculation and for homework, and they send that to me. Even if they had problem, that's okay, because I want to see if you have any problem. Yeah. So, but if you are not working on that, I can't help you. Yeah. That's in your actually court. Right now, you have to do your job. I can't do anything else. I send you anything that I could. I solve a lot of example for you guys, send that to you guys, and just I'm waiting for you guys, and that's your time. Please do your job. I cannot accept any excuse for that. You had 2 days of weekend. Do you know what I mean? I know you have other stuff as well, but you actually accepted to go with all these units that you picked and the other stuff that you are doing. So please do your job and do it fast. Today, I'm giving you new stuff that you will see a lot of code that you have to go through these codes. So if you are not working on the last one, you have to do double time to be able to get this done. And I'm sure that it should be even harder. So please do your job and send that on time. Otherwise, I cannot help you. Okay, so let's start today. This is always, sometimes I'm put inside the slides because we need this, and you have access to this areas and diameter and everything. Today, I'm going to talk about bond and development length. So the easiest part that I can give you information to understand what does it mean. It means that something like this. Imagine you have a nail, yeah, just inside piece of wood. So in order to take it out, how much force do we need to take it out? If the penetration is just 1/8 of an inch, do you need more force to take it out? Or if you have 2 inches in? So for sure, if you have 2 inches uh, embedment or penetration inside this wood, you need more force to be able to remove this. If the diameter of this nail is 1/8 of an inch, or if it's 1 inch, which one you need more force? For example, for sure, whenever it's thicker, yeah, when diameter is bigger, you need more force to be able to take it out. That's it. If you got this, that's the meaning of development length and bond. Yeah. So if we have rebar inside the concrete and you want to take it out, the diameter is important, the bonding between these two important, a lot of stuff. So we call that development length, that the length that we need to make sure that the rebar can reach to Fy, like here. We don't want to this nail to come out. We want to make sure that if you pull it out, the nail will reach to Fy. So it start yielding instead of coming out. Yeah. So development length for the rebar is the minimum required length that rebar will reach to Fy if we start pulling that out. That's it. That's the meaning of this development length. And the bond between rebar and the concrete is very important. At first, they were using they used just the smooth bars. There was no actually deformed bar that we have right now. So a long time ago, they had just smooth bars. So a smooth bar, after they pour concrete on top, if it wasn't that clean, it had some dust on top or is rusted, so it couldn't make that good bond between the concrete and the rebar. And especially whenever you had moving load, like a bridge, or even at home when you are walking, you can sometimes you can feel the movement of the floor. So in that case, it means that the beam will go up and down, up and down. So the rebar can start just losing the bond between the concrete and the bar. So in this case, when it's bent like this, you can see the length of the bar was this black part. And when it's getting bigger, so you will get some crack on the beam. So you will get some part that has no rebar. It means the rebar is slipped inside that hole, because the bond is gone after a few years, after just that loading that can vibrate the beam. So they noticed that a long time ago, they tried to come up with a solution. How can we stop this? Because if it start moving, you will get crack. The rebar cannot reach to Fy, because you put more load, it will move more. If put more load, can move more. So you will get crack and you will lose the beam. The rebar cannot reach to Fy because nothing is here to hold it and create that development length. Yeah. Because of that, they came up with this solution, 180-degree bend at the ends. It helped a lot. It helped a lot, because when it wants to go down, this part will be stopped with the concrete. So even if we lose the bond, you still, these two heads will hold this and the rebar can reach to Fy. But after a while, they cannot use this always everywhere. Whenever you have beam to column connection, this kind of bend will create a lot of extra rebar, and with a lot of other rebar for the column and the beam that we have, it will get some space and we cannot pour concrete. So because of that, they came out with deformed bar. So the bar has up and down on the surface. So those can go inside the concrete and increase the bond. So that's the bound part. And development length, I told you, minimum required length to make sure that the rebar can reach to Fy. So that's important thing that we should carry. So how can we calculate that? They did a lot of tests all around the board. And ACI actually put them together, all the results, and during the past 100 years, they collect all this information, and a lot of committees work on those, and they finally made some advices that right now we can use them as an engineer. All of us, we can use those stuff in our design. So we know that we have different kind of elements. uh, Columns that you can see, this is one of the rebar columns for the one of the bridges. So those are huge, and then they have to tie them together on the ground and then stand them up by crane and just use them as a column. So columns are in compression. Look at this. This is column with tie bars, and this is column with the spiral. So any kind we can use. So if you want to find the development length at the time of you have a splice between the first story column and the second story. So you have a roof. Let me plot this. This might be important. Consider this is your roof, yeah, or the beam for this level, for the floor that we have. This is column on the second story. This is the column from first story. So the rebar from this part should go inside this and go here and inside this, and then splice them for the second floor, yeah, something like this. Yeah, I made that very simple actually to understand. So splicing at the second. So what is this length? How much development length do we need? So we can go with the compression because that's concrete columns, and concrete columns are in compression. If you as a designer, based on the earthquake, you notice this column has a huge tension, then you will go with tension development length, yeah, otherwise with compression development length. So you as a designer will know in future. Right now in this class I will let you know that we are talking about the column, and under talking the column in this class, assume that it's under compression. So if you have column sitting on the footing, so you have a footing here and you have column sitting on this part, yeah, this is the column. So the rebar of this will go inside the footing. So how can I calculate the length of development length here? Based on development length in compression. It means that if you put load on this in compression, this minimum length will give us enough length to be able to reach to F5 for those rebar. If those are short, then they cannot do their job, yeah, in compression. Do we need development length, longer development length in compression or tension? For sure in tension, because compression will help us to actually keep this. But in tension, when you pull this out, so the whole rebar just can help us to stay intact with the footing or whatever we have, yeah, when it's in tension. But in compression, concrete and rebar, both of them can help us. In tension, we assume that concrete cannot do anything. Okay, one question. What's the question?
So the formula on the bottom is for rebar and compression, and the one on top is for tension?
No, 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 no. I will go through them, but that good question. No. This part is just compression. This slide is just compression. I separate them completely. And I will go through all of them one by one. Just I'm giving you information. If you have a connection between columns, you might go with the compression development length. If you have column to the footing connection and you know it's in compression and tension is not that big, most of the time when there is no earthquake, compression is for sure will govern all the loadings in columns. So so assume that we know that the compression is the loading on our column, and we are going to calculate the development length. So first of all, we are showing that with LDC, development length in compression. L for the length of development length in compression. Yeah. So what's the equation? Based on the equation, I wrote this code for you guys. If you have the code ACI, go to this code and you can find these equations. Okay, maximum of these two. Yeah, so you have to calculate this. You have to calculate this and pick the maximum of those two as the minimum development length required based on the ACI. Okay, so let's start with all these parameters that we can see here. Lambda, we know that from the past, yeah? That's one for normal concrete and 0.75 or 85 for lightweight concrete. And in this class, we are working on normal concrete. Our lambda is 1, unless I give you the lambda is 0.75 or something else. Okay. What Fy? Fy is the yield stress strength for the bar. vertical bar. That's on the ground right now. It's not vertical because they are tying the rebar. Then with the crane, they are making that vertical. But the main bar Fy, yeah, that's the rebar that you want to find the development length for that. That's Fy. What is dB? dB is the diameter of the rebar that you are calculating the development length. For example, here you have number 11, two number 11, one number 11, it's your bar. For number 11, your dB is 1.41, yeah, for number 11. So Fy, dB, lambda, so far we know that. F prime C, concrete 28 days strength, yeah, PSI, PSI. So the only part that we don't know yet is CR. So you can see it here, yeah. CR is for the reinforcement confined within a spiral reinforcement. What does it mean? When you have the development length, at the development length, if you have a column with a spiral, and the size of the spiral pitches, yeah, should be 4 inches, and the number of the spiral is 4, number 4. So this type, this spiral around this is looks like a spring. They are just tying like a spring, yeah. So they call that a spiral. A spiral number 4 with the pitch maximum 4 inches. Then you can use that CR is equal 0.75. So it can reduce the length. Look at this, 0.75 times this is your length. So if you use these two, number 4 spiral with maximum pitch equal 4 inches, then you can reduce that 25%. This length will be reduced, 0.75. Or if you have rectangular column with tie bars, the tie bar spacing is 4 inches, yeah, the same as the other one, yeah. So in both cases, actually, when you are using these two, you can read this stuff actually, yeah, the code. It's, you don't need to remember that, just you can read that code. So put all those stuff in this equation and find this number, find this number. So in these two cases, you can use 0.75. If you don't know or you don't have this information, in this case, go with 1. So CR is equal 1 if we don't have these two cases, a spiral with this diameter, with this pitch, tie bar with this number and this spacing. If you don't have this case, consider equal 1. If you are in this case, you can reduce that length 25%. You can use 0.75. That's it. Yeah. So calculate this, and find that actually LD. If you are bundling bars, look at this over here, we bundle 2 bars, yeah, because we had a lot of rebar. So if we actually spread them, there is not enough space between those two to be able to have gravel going between and go to the that cover. So in that case, you are bundling them, sometimes 3 bars, sometimes 4 bars. If we are bundling 3 bars, just go with 1 dB in order to find the development length for bundled bar, means 3 rebar together. Let me show that. Oh, sorry about that. I think I stopped this. I wanted to do something else. Okay, if I go with 3 bundled bar, what does it mean? It means that 1 bar is here, yeah, that's one of these rebar. Then another bar, I will put that here, and the third one, I will put that here. We call this bundled bar, 3 bars. If I go with this bar, I will add another here. So in this case, how can I find the development length in compression for this bundle bar? I have to calculate for actually that dB and times 1.2, yeah, for a 4-bar bundle go with 1.33 LDC. So calculate that with for 1 bar, yeah, for 1 bar, whatever it is, number 11. Then increase that 20% if you bundle 3 of those. Increase that 1.3% if you have, yeah, that's it. So it's not that big deal. Just we have to do this based on the code. Okay. Sometimes we calculate, for example, we calculate for 20 number 11 bars, we calculate 20 point something square inches rebar is needed for this column. And when we pick the size of the bar, instead of 20, we are using 25 square inches. So means that required is 20. But when we picked the rebar, we picked more. We used 22 square inches, 25 square inches, something more than that. So it's required based on the calculation. You need 20 square inches, for example. Then you pick the rebar, you are using 18 number 11, and you calculate this, you will get 22 square inches. In this case, the code will allow us to reduce this length based on this one because we used more. So required 20 divided by provided 22, for example, that's less than 1. That number times that the maximum of these 2 times L would be your final development length required. So we can use this reduction factor based on the code. AS required. Yes, what's the question?
Is that reduction factor only for bundles?
No. That's based on your design. It should go for any kind of development length in compression. Good question. No. So you design the column, you need 20 square inches, but you pick the size of the rebar, and then you notice that you use 22 square inches. So you can go with 20 divided by 22 times LDC, final LDC between the maximum of these two. Then that's your minimum required development length in compression for your column. Clear, everybody? If you have any question, please stop me and let me know. Otherwise, I think you got it and there is no problem with this part. Even if I pass that slide, if you still have question on the past slide, let me know. I will back to those and I will start reviewing those one more time. Then go after development length in tension. So tension, we have a straight before or we have bent. If we bent the rebar, in this case, we are going just with a straight, yeah, with no bend. It means that, for example, let me show you. Assume that we have a huge column, that's a column, and you have a beam is connected to this column, yeah? And the rebar that you have is here. This is top rebar in tension, yeah? Bending moment this side, you will get tension on top bar, negative moment, tension. So development length, you should check this inside the column. That's the development length. That's from here to here, development length inside the column. And also if you are going to cut the bar inside the beam, imagine if you want to do this. So this is your development length as well. Don't actually think why they are not equal. They must be equal. Development length at each point for tension should be equal inside the column, outside of the column. So you can go straight, yeah? So I have to check if I have enough room, LD development length with no other actually stuff. LD is in for tension, LDC for compression. It means that a straight length like this, sometimes the column is not that big, so you have enough room for this because column is big. Sometimes the column is not that big, so you have a huge beam sitting on almost a small column. So in this case, for sure, you don't have enough room for a straight length. Then the next slide, we will go with the bend rebar. So we can bend this rebar inside the column. So in this case, we need a smaller length. Yeah, just
Uh,
I show
Professor,
this. Yes,
is L sub D the development length?
this LD, yes.
Okay.
This is your LD for tension. Look at this, development length in tension. A
Okay.
straight deform does. What's the straight means? This bar will go inside the column with no bend. Inside the beam with no bend. This one, inside the beam straight, inside the column, because the column is small, a straight line. If I go straight, I need this long, but we don't have that concrete here for the column. Then I have to bend this. So I should have another slide for development length in tension, not for a straight, for actually hooked bar. Yeah, when we bend them, we call them hooked. So in the next slide, we will learn how to calculate that one. Is that clear for everybody? What's the difference? Why I mentioned straight here? Because in other one, I'm going to show for when you don't have enough room for a straight bar inside the column, then what can we do? Or inside the beam, what can we do? Yeah. So for another part for the beam, consider if you have a actually column with a cantilever. Yeah, that's a cantilever. So, and that's the column and cantilever beam. So when you have this rebar here, you have to check a straight bar development here if you have enough or not. Then a straight for inside the beam if we have enough room or not. If we don't have enough room, then we have to bend this here and bend this that side or do something else that we will learn step by step. Okay. So let's go after the equation. This equation, actually today, I'm giving you a lot of information based on the code. And it's not that easy to get them in the first place, but you have to go through the examples, solve the examples to make sure that you can read this. These parts that you can see here, you have to find them in 2 or 3 pages of code. So I spent time to find all those required code that you need, put them in one slide. So it's easy to understand this rather than if you go with that. But in future, for sure, when you read that ACI, then your eyes is familiar with all those equations, how to find that, which part is you should look after this stuff. So you have to go to the that part, to that code as well. So at this slide is good for the start. Okay, so that's the code, ACI 25.4.2.3. That's the main equation. And you can see that's a lot of parameters. Those are just based on tests, a lot of tests. Okay, first of all, CB plus KT R divided by DB must be greater than or less than or equal to 0.5. Less than or equal, it must be. So if you calculate this based on what we will learn here. If you got 2.6, then instead of this, you should consider 2.5. Just remember this. These are important. Whenever you can see this limit, it means that this part cannot pass that limit. If you got more than that, go with that 2.5. Lambda, we know that. dB, diameter of the river that you are going to find the development length intention for that. That's diameter. Yeah, one of these river. Yeah, one of these river intention. That's diameter of this river. If you have different rebar, you have number 11 and number 10. So you don't want to actually go with number 10, go with the bigger size because you will get the longer development length. Yeah. So if you have mixed rebar, go with the bigger rebar to calculate just one time. To go with different one, to go with number 11, go with this much, number 10 with that one, that's hard in the field. Because if they bend them by mistake, instead of number 10, they go with number 11 and change that, those are wrong. And because of that, we will go with the bigger size of the rebar. Okay, let us start with this. What's the CT? That's casting position factor. What does it mean? If you have a rebar that it has more than 12 inch of fresh concrete. So over here, this rebar, do we have more than 12 inches of fresh concrete underneath? No, because that's bottom bar. Yeah, so for bottom bar, we have no such a case. You have 2 inches, 3 inches, not more than 12 inches. But if we are going and talk about top bars, imagine we have negative moment. Yeah, negative moment are top bar. So in that case, you have more than you might have. Yeah, depends on the height of the beam. If the beam is 3 feet, so for sure you have more than 12 inch. If you have 2 feet, the top bar, you will get more than 12 inch of concrete below these. So yes, in this case, if you have more than 12 inch, this factor is 1.3, and you can see it means that 30% can increase your LD, whatever it is, times 1.3. So it can increase 30%. That's too much. And why we are getting this? Imagine you have forms here. These are forms, and you are going to pour concrete for this beam. Yeah, form and pour concrete, and then vibrate that. Why we are vibrating that? Because we want to get rid of the air inside the concrete. When you vibrate that, the air will go on top. So when you pour up to here and vibrate that, all the air will come to get out from here. Yeah. And then because we have this reward, the air will be actually stay here, will be trapped here. Yeah. And when you have more than 12 inch of fresh concrete, you have a lot of air bubbles. Those air bubbles will come and will stay here. Then you will lose the bond between concrete and the bar. Yeah. So you have a bar with air, no concrete. So you will lose that bond, and you cannot get the development based on the bond that you thought. So in this case, based on the code, based on the lot of tests that they did the vibration, and then they pulled them out by force, and they compared the result, then they come up with this number. So increase 30% if you have more than 12 inch of fresh concrete underneath. Yeah, I hope you got it, why we got this. Other situation, if you have less than 12 inch one, there is no need to increase that. The air bubbles that you will get is not that much, so it cannot reduce that the bond between the concrete and the bar. So that's the reason behind this, why we add this actually 1 and 130. Another part, this diagram is for this case. You can see I show that here. Yeah. So this one is for it. So the other part is epoxy coating factor. What is epoxy? Epoxy is kind of paint, or kind of a mixture of glue and paint, that when the rebar is in environment that has a lot of stuff that is bad for the bar, for the rebar, then we cover that with something to protect the rebar. In most of the actually bridges or structures near the ocean, or at the place that it's hot and you're close to the sulfate or chloride, in that case, we are going to use this epoxy coating. And if you drive somewhere that they are doing the bridge construction, if you see purple rebar, or orange rebar, or green rebar, those are epoxy coated bars. Yeah, so just remember, if you see colored rebar from far, it means that it's covered with a coating to protect them against the environmental actually problem for the bar. So if we cover that with that epoxy coating, and this cover, look at this, just not underneath the tie bar, the stirrup, no, from bottom of the bar to the face, it can be on top or the bottom. This is for tension bar at the bottom. You can have something like this for tension bar on top. Yeah, everything should be for the bottom or top, doesn't matter. If you have more than 3 times of the bar size of the bar, which bar? The bar that is bigger. If you have combination of 10 and 11, go with 3 times of the diameter for the big bar, number 11. And the spacing is less than 6 times of dB. 6 times. The free spacing, the clear spacing is less than this. And the cover here is less than 3 times of dB. So you have to go with 1.5 if it's epoxy coated. Yeah. If you have epoxy coated, but this one is more than 3 dB, yeah, greater than 3 dB, or if this one is greater than 6 dB, yeah. So in that case, what can we do? Can I go with other actually cases? So in that case, if it's epoxy coated, it's up to the designer to pick the number. So for me, I will go with the critical one. Yeah, whenever, because you covered the rebar with the paint, it's very slippery. So it's up to you to go with which part. So these are just recommendations based on the code. But if you are not happy with that, you can go with the maximum. Instead of go with 1 point something, you can go with 1.5 to increase that. So for all other epoxy coated or zinc epoxy dual coated bars, you can go with 1.2. It means that you have more than this 3 dB and more than this 6 dB. In that case, you can go with 1.5, 1.2. So you can reduce that. It means it will increase 50%. Look at this, CE 1.5. It means that you are increasing the length. So if it's uncoated, in this case, you can go with 1, just regular rebar. Just remember, the multiply of this CT times CE shouldn't be more than 1.7. So you calculate that one. You calculate this one. Then you find the CT times CE. If it's more than 1.7, use 1.7. Instead of these two, you do not use 1.3 times 1.5. No, if it's more than 1.7. Instead of these two, use 1.7. Just this is the things that you have to check. Yeah. If it's more than this, go these two equal 1.7. Please pay attention to all these stuff. These are important part of the code that you must follow. So another thing is CS, reinforcement size factor. It's not that hard. If you are the rebar that you are working on, development length is number 6 and smaller, go with 0.8. Yeah, that CS 0.8. If it's number 7 and larger, go with 1. And I put a note here that I showed here for positive moment, but if it's negative moment, all the rebar should be on top. But still, you can follow the same system. Yeah, and lambda, lightweight concrete and regular concrete. So we already know that. What is CB here? Spacing or cover dimension. What does it mean? CB is minimum of S1, S2, or S3 divided by 2. What are those? S1, as I mentioned, I'm showing this for positive bar. But if you're calculating development length for the tension on top for negative moment, all this stuff will go on top. Just rotate this 180. Yeah, rotate this 180. Everything is exactly the same. S1, the first, because it's similar at both sides, the first rebar center from the face of the beam. That's
Professor?
your S1. Yeah. Yes.
When it says min S1, S2, S3 over 2, do we pick the minimum of those 3?
That's correct.
Okay.
Calculate, find these 3 and pick the minimum of those as your CB.
Okay, thank you.
Okay, perfect. So that's your S1, center to the face. What's the S2? Center to the bottom. Or if you turn this around, should be center to the top. Yeah, S2. So I showed that with positive. For negative, should be on top. So that's S2. S3, center to center of the rebar, divided by 2. S3 divided by 2. That's it. That's it. So what is this? The other one, KTR, it should be transverse reinforcement index. That's KTR. And is equal 40 ATR divided by S times N, SN. Okay. What is ATR? ATR total area of the stirrups legs. Yeah, total area. For example, if you are using number 3 with 0.11 square inches and you have 3 legs, so 3 times 1.11, 0.11, you will get ATR is equal 0.33. Yeah, like before, total cross-sectional area of all the legs. So over here, we have 2 legs. Yes, what's the question?
For the CB, it says spacing or cover dimension. So do we have to pick the minimum if the cover is smaller than the spacing? Oh, that's S2. I'm sorry, I didn't see S2.
Yeah, those are different. Yeah, S2, S1, S3 divided by 2. Yeah, between these 3, pick the minimum.